Okay, let's unpack this. Imagine, just a century ago, our entire concept of the universe was radically different from today.
Radically different. It's almost hard to believe.
Yeah. And the incredible story of how we figured out how old is the universe.
Hmm.
Well, it isn't just about finding a number, is it? It's really a testament to, I guess, human ingenuity and just sheer persistence.
Absolutely. We're talking about grappling with scales of time and distance that are almost impossible to truly comprehend.
They absolutely boggle the mind, and it's all driven by this relentless human curiosity, this need to know where we came from, maybe where we're headed.
Hmm.
It's a journey filled with surprises, lots of aha moments, and I think it really promises to shift how you see, well, everything.
What's truly fascinating here, I think, is that this quest isn't merely about attaching a numerical age to the cosmos.
Right.
It's a story about the remarkable evolution of human thought itself. It's about the continuous refinement of our scientific tools, our instruments,
Yeah.
and a profound ongoing shift in our perspective on our place in this vast universe. Our most advanced telescopes, they're essentially powerful extensions of our own senses, aren't they?
That's a great way to put it.
They let us peer further and further back in time, unraveling some of the deepest, most fundamental mysteries about our existence.
And that profound journey is exactly our mission for this deep dive. We're going to explore how our understanding of the universe's sheer scale, its incredible age, how that's been dramatically reshaped over time. We'll look at the groundbreaking telescopes that literally made these discoveries possible, things we couldn't have dreamed of before.
Yeah, the enablers.
And what the very latest observations, from things like Webb, are revealing about our cosmic origins and maybe even our potential future. We've gathered a stack of sources, articles, research, even some fascinating bits, and we're going to pull out the key nuggets of knowledge for you.
Distill it down.
Exactly, guiding you through this captivating story of scientific discovery. So, buckle up. Right, first things first. To truly grasp the magnitude of where we are now, we need to rewind the cosmic clock. But not billions of years. Just about a century.
That's a crucial starting point.
It's almost impossible to imagine now, but for hundreds of years, our cosmic neighborhood, just our own Milky Way galaxy, was widely considered to be, well, everything, the entire cosmos.
That was the picture, yes.
Yes.
Our sources confirm that just 100 years ago, what we now casually call distant galaxies, they were thought to be much, much closer.
Like inside our own galaxy close?
Potentially, yes. Or perhaps just on the fringes. The prevailing scientific consensus before, say, 1923 was strikingly different from today. Almost quaint, you could say.
Right, so those faint, fuzzy patches of light, the nebulae.
Exactly, the nebulae. Astronomers saw them, of course, but they were largely believed to be vast clouds of gas and dust within the Milky Way, maybe lit up by stars, maybe areas where stars were forming. But the key point was the location within our own galaxy. The dominant idea was these island universes, as they were sometimes called. There were maybe smaller systems, star clusters perhaps, but all contained within our grand spiral.
So our galaxy was the whole universe, essentially.
That was the effective boundary of the known universe for most scientists at the time.
So what was the real hurdle then? If they saw these fuzzy things, why didn't they think maybe they're further away? Was it just the lack of powerful enough telescopes, or was it something more conceptual?
It's a mix, really. This limited perspective wasn't because astronomers back then weren't brilliant, they absolutely were, but it fundamentally reflected the boundaries of the available observational technology, yes. And crucially, there was a lack of definitive, unambiguous evidence that could challenge this sort of galactocentric view.
Galactocentric, I like that.
Yeah. Imagine, if you will, the universe drawn on a dinner plate, and our Milky Way fills that entire plate. Without the tools or the data to see beyond the rim of that plate, it becomes incredibly difficult to even conceive of a larger table, let alone a whole cosmic kitchen filled with other plates, other galaxies.
It's like that island analogy you mentioned earlier, thinking your island is the only landmass.
Precisely. You think your island is it until someone builds a ship powerful enough or spots land on the horizon, proving otherwise. This pre-1923 worldview really underscores how truly groundbreaking the next steps were.
Right.
And it highlights something fundamental about science. Our understanding is always provisional. It's always ready, or should be, to be overturned by new, compelling evidence.
Okay, here's where it gets really interesting. This is where the universe quite literally just exploded in scale for us. Our sources pinpoint 1923 as the watershed year, a moment Edwin Hubble, like a name that just echoes through astronomy, doesn't it?
Absolutely, the giant in the field.
He completely reshaped our understanding, moved us from that single cosmic island to a vast, vast cosmic ocean.
That's right. Hubble's meticulous observations were key, particularly his study of a special type of star, Cepheid variables, within some of these nebulae.
Cepheids. Okay, what's special about them?
They are incredibly useful cosmic mile markers. Cepheids pulsate, they get brighter and dimmer at a very regular rate. And crucially, the speed of that pulsation is directly linked to their true intrinsic luminosity, how bright they actually are.
Okay, so if you know how fast it pulses.
You know how bright it really is. Then, by measuring how bright it appears from Earth,
you can calculate the distance, like knowing a light bulb is 100 watts and seeing how dim it looks from far away tells you how far away it is.
Exactly. It's a cosmic yardstick. And Hubble used this yardstick to measure the distances to several key nebulae, including the Andromeda Nebula.
And what did he find? Were they close?
Not even remotely close. His measurements were staggering. They showed, unequivocally, that many of these nebulae were not clouds or star clusters within the Milky Way at all.
What?
They were entirely separate galaxies, vast collections of billions, sometimes trillions, of stars existing hundreds of thousands, even millions of light years beyond the edge of our own galaxy.
Millions of light years. So Andromeda wasn't a cloud inside our galaxy. It was another galaxy entirely.
A whole other galaxy, far, far away. This wasn't just, adding a few more entries in the catalog. It was a complete, instantaneous redefinition of cosmic scale.
I can only imagine the shockwaves in the scientific community. The whole universe just inflated overnight, conceptually.
It truly did.
Yeah.
We went from thinking we were basically alone in our island universe to suddenly realizing we were just one galaxy among, well, countless others, maybe billions.
Countless island galaxies scattered across this immense cosmic ocean.
Precisely. And that single observation, that single realization dramatically opened up the entire field of extragalactic astronomy. It launched humanity on this incredible journey to understand a much larger, much more complex universe.
And a much older one too, right? Because seeing those distant galaxies meant their light must have been traveling for
Immense periods of time, exactly.
Yeah.
Millions, or as we'd soon discover, billions of years.
So this discovery didn't just change our star charts. It fundamentally altered our perception of our place in the cosmos.
It really did. And it laid the intellectual groundwork for huge ideas like the Big Bang Theory. If the universe is full of galaxies and they seem to be moving apart, well, that implies a beginning, doesn't it?
Yeah, it points backwards to a starting point.
But this amazing revelation immediately highlighted a new, very practical problem, a challenge right here on Earth, literally.
Okay, what was that?
How do we actually study these incredibly distant, incredibly faint objects effectively from down here, looking up through our own atmosphere?
Right. So after Hubble blows the doors off the universe, you might think, okay, let's just build bigger telescopes on the ground. We have some huge ones now. So why did we eventually decide we had to go to space? What's the fundamental limitation down here?
It comes down to the air we breathe, our atmosphere. Essential for life, obviously. But for astronomers, it's a real headache. It's a turbulent, dynamic blanket of gas that distorts the light coming from space.
The twinkling stars effect.
Exactly. That twinkle might look pretty, but for an astronomer trying to get a sharp, detailed image of a galaxy billions of light years away, it's like trying to take a crystal clear photo through constantly rippling water.
It blurs everything out.
It smears out the fine details. This atmospheric interference is caused by varying air densities, temperature changes, moisture, pressure fluctuations. It significantly limits the clarity, the resolution of even the best ground-based telescopes.
So it's not just about light pollution from cities, which we hear about a lot.
Light pollution is a big problem, absolutely. That's why observatories are built in remote areas. But even in the darkest, most remote place on Earth.
Like deserts or high mountains. The sources mention places like Sinai for clear skies.
Yes, exactly. High, dry locations are much better. They minimize water vapor and put you above some of the densest, most turbulent air. But even on the highest mountain peak, you're still looking through miles of atmosphere.
The blur is still there, like trying to read tiny print through wavy glass or that heat haze off a road in summer.
That's a great analogy, the heat haze.
Yeah.
It fundamentally limits how sharp an image you can get from the ground, even with sophisticated techniques like adaptive optics, which can correct for some blurring in real time.
Yeah.
It's still not perfect, and it's complex. We basically hit a ceiling in our ability to see the faintest, most distant, most detailed things from Earth.
So if the atmosphere itself is the ultimate barrier,
Then the only way to get past it is to get above it.
and that led to the, well, audacious idea. Let's put telescopes in space, escape Earth's gravity, escape that shimmering blanket of air altogether.
It was the logical, albeit incredibly challenging, next step. The only way to get truly clear, pristine, undistorted views of the cosmos. To see things without that atmospheric filter messing things up.
And the advantages were huge, right? Not just clearer pictures.
Oh, much more than that. Firstly, yes, unparalleled clarity and resolution. No atmospheric turbulence means incredibly sharp images. Secondly, zero light pollution from Earth. Total darkness.
Perfect viewing conditions.
But perhaps even more importantly, space telescopes allowed us to observe across the entire electromagnetic spectrum.
Because the atmosphere blocks some kinds of light.
It does. It acts like a filter. It absorbs a lot of high-energy ultraviolet light and critically large portions of the infrared spectrum. Light carrying crucial information from the cosmos just doesn't make it down to the ground.
So in space, you can see in UV, you can see in infrared wavelengths that were basically invisible from Earth.
Precisely. Telescopes could be designed specifically to detect these previously hidden signals. It wasn't just about getting a sharper view, though that was immense.
It was like suddenly gaining new senses, wasn't it? Like taking off smudged glasses, but also being able to see colors you never knew existed before.
Exactly. It opened entirely new windows onto the universe. We could suddenly perceive phenomena that were completely hidden before: superhot gas emitting UV, cool, dusty, star-forming regions glowing in infrared. It fundamentally changed the kinds of questions we could even ask about the universe.
Because we could suddenly see things relevant to those questions.
Yes. And with that realization, humanity embarked on the monumental task of designing, building, and launching these eyes in the sky. And the first great one, the one that really captured the public's imagination, was Hubble.
Right, the Hubble Space Telescope. Launched in 1990, after decades of planning, it quickly became, as our sources say, the most important space telescope, our premier eye on the cosmos, gathering data mainly in visible and ultraviolet light.
Hubble was truly revolutionary, not just a scientific instrument, but a symbol of human ambition and exploration. It was a proof of concept, demonstrating the immense value of doing astronomy from space.
It wasn't all smooth sailing at first, though, was it? There was that issue with the mirror.
That's right. A tiny, tiny flaw in the shape of its main mirror, less than the width of a human hair, initially resulted in fuzzy images. A huge disappointment after so much effort and cost.
But they fixed it, those incredible astronaut repair missions.
Yes, a series of daring spacewalks installed corrective optics, essentially giving Hubble eyeglasses, and the results were spectacular. It transformed Hubble into the scientific powerhouse we know today.
And it didn't just provide data for scientists. It gave us those breathtaking images, didn't it? The pillars of creation, deep field images. It made astronomy accessible and awe-inspiring for everyone.
Absolutely. It redefined public engagement. Its longevity is also remarkable, far exceeding its initial design life, thanks to those surfacing missions. And the sheer volume of data, over 1 million observations our sources note. Just incredible.
And beyond the pretty pictures, Hubble delivered some truly mind-bending science, right? Especially about the centers of galaxies.
Yes, fundamentally altering our understanding of galactic architecture. Hubble provided crucial, compelling evidence confirming something astronomers had suspected. That galaxies, including our own Milky Way, aren't just random collections of stars. They revolve around incredibly massive objects at their cores.
Supermassive black holes.
Supermassive black holes. Exactly. Hubble could observe stars and gas clouds whipping around the very centers of galaxies at incredible speeds.
They're fast to be orbiting just other stars.
Far too fast. By measuring those speeds and how tightly packed the orbits were, scientists could calculate the mass needed to hold everything together gravitationally. And the only thing that fit the bill was an immense, concentrated mass, millions, sometimes billions of times the mass of our sun, packed into a tiny space, a supermassive black hole.
Wow. So these things are like the gravitational anchors for entire galaxies.
That's a very good way to think about it. They play a fundamental role in how galaxies form and evolve. They influence the gas, the stars, everything around them on enormous scales. Hubble showed us that our own Milky Way orbits such a black hole called Sagittarius A.
And this leads to that rather stark phrase from our sources. You are destined for the drain. The black hole, it's no use. That sounds final.
It does sound quite dramatic and maybe a bit fatalistic.
Yeah.
It's important to put it in cosmic perspective. It's not suggesting our solar system is about to get sucked in tomorrow. We're orbiting Sagittarius A safely, about 26,000 light years out.
Okay, phew.
But the phrase captures the immense, inescapable gravitational power of these objects on galactic timescales. Over billions and billions of years, they are the dominant gravitational influence. The source also touches on galactic collisions, like the future merger of the Milky Way and Andromeda.
Which Hubble helped us understand is coming.
Yes. And observing these processes helps us understand the long-term fate of galaxies. So while individual stars aren't imminently drained, the overall structure and eventual fate of galactic matter is profoundly shaped by these central black holes. It is like a giant cosmic whirlpool, shaping everything over eons. A powerful, if unsettling, image of gravity's ultimate dominion.
So Hubble opened our eyes, showed us the scale, the galactic structure of these central monsters, but there were still things it couldn't see, right? Deeper secrets, earlier times?
Precisely. Hubble operates primarily in visible and ultraviolet light. But the very earliest light in the universe, from the first stars and galaxies, has been stretched by cosmic expansion into infrared wavelengths, and there's also a lot of cosmic dust that blocks visible light.
So we needed an infrared eye in the sky.
We needed a bigger, colder, more powerful infrared eye in the sky to peer back even further through the dust and across the vast stretches of cosmic time. And that led to the development of Hubble's successor, or perhaps its more advanced cousin.
The James Webb Space Telescope, JWST, launched just a few years ago, Christmas Day 2021. This is the next generation, isn't it?
It really is a marvel of engineering, and its location is key to its power. JWST isn't orbiting Earth like Hubble. It's way out at Lagrange Point 2, or L2.
L2. That's about 1.5 million kilometers away from Earth, nearly 1 million miles.
That's right, much, much further out than the moon. Our sources mention L2 being generally stable, around 55,000 kilometers in some contexts, but Webb orbits around this point at that greater 1.5 million kilometers distance.
Why so far out? What's special about L2?
L2 is a gravitationally stable point where the poles of the Sun and Earth balance out in just the right way. It allows Webb to stay in a fixed position relative to both, using very little fuel.
Ah, so it can just hang out there.
Exactly. And crucially, from L2, it can keep its back to the Sun, Earth, and Moon simultaneously. Its massive sun shield blocks their heat and light.
Keeping it cool.
Incredibly cold, which is absolutely vital for an infrared telescope. Infrared is essentially heat radiation. To detect faint infrared signals from distant galaxies, the telescope itself has to be extremely cold, otherwise its own heat would swamp the signals.
Okay, that makes sense. So it's a silent, ultra-cold sentinel out there, far from Earth's heat, ready to pick up those faint, ancient heat signals.
Perfectly put. Its location and temperature control are fundamental to its mission.
And that mission relies on infrared light. You mentioned the earliest light is stretched into infrared. Can you unpack that a bit more, the red shift?
Sure. It's a direct consequence of the universe expanding. As space itself stretches, the wavelength of light traveling through it also gets stretched. Think of a wave drawn on a rubber band. As you stretch the rubber band, the wave gets longer. Light waves behave similarly. Light that started out as high-energy ultraviolet, or visible light, from the very first stars billions of years ago, as it traveled across the expanding universe to reach us, its wavelengths got stretched longer and longer, shifting it down the spectrum towards the red, and eventually deep into the infrared.
So to see that ancient light, you have to look in infrared. It's not visible light anymore.
Correct. Hubble couldn't see much of it. JWST is specifically designed for it. And there's another huge advantage to infrared.
The dust.
The dust. Huge clouds of cosmic dust block visible and UV light very effectively. They hide regions where stars and planets are forming. They obscure the centers of galaxies.
Like trying to see through thick smoke.
Exactly. But infrared light, with its longer wavelength, can penetrate that dust much more easily. So JWST can peer through these dusty veils and see things that were completely hidden from Hubble.
So it's like having cosmic X-ray vision and a time machine combined.
That's essentially its superpower. It bypasses the dust and detects the redshifted light from the dawn of time. It lets us see the universe's baby pictures, light from an era we've never directly observed before.
Incredible. So what are the big questions this $10 billion marvel is trying to answer? Our sources mention two main goals. First, seeing the universe when it was only about 100 million years old, looking back almost 13.7 billion years.
Yes, the quest for first light. This is about understanding how the very first stars and galaxies ignited. After the Big Bang, the universe cooled and entered a period called the Cosmic Dark Ages, filled with neutral hydrogen gas, basically a fog.
Dark and foggy.
Until the very first stars formed likely massive, incredibly hot stars. Their intense radiation started to ionize that hydrogen fog, clearing it out in a process called reionization. JWST aims to capture light from those very first stars and galaxies to see how they formed and how they transformed the early universe.
Witnessing the cosmic dawn, amazing. And the second goal is maybe even more profound, looking for signs of life on exoplanets, analyzing their atmospheres.
Indeed. JWST can study planets orbiting other stars, or exoplanets. One technique involves observing the starlight filtering through a planet's atmosphere as it passes in front of its star. Different gases in the atmosphere absorb specific wavelengths of light, leaving a unique chemical fingerprint.
And some fingerprints might suggest life, biosignatures.
That's the hope. Certain combinations of gases, like oxygen and methane existing together in large amounts, are hard to explain through geology alone, at least based on our understanding from Earth. Finding such biosignatures would be incredibly strong evidence for biological processes at work.
Wow, just finding microbes would be revolutionary. But the sources even mention finding planets we can live on in the future, billions of them. That sounds like science fiction.
It's certainly looking very far ahead. Finding planets with biosignatures is the immediate, albeit extremely challenging goal. Identifying planets that are genuinely habitable, in the sense of being Earth-like, is another step. The idea of finding billions or planets we can live on implies leaps in technology and understanding that are, well, currently speculative. But it speaks to the ultimate ambition, the long-term dream driving some of this research.
It definitely captures the imagination. What happens if we do find life or see those first galaxies? It changes everything.
It potentially redefines our understanding of cosmic history and our own place within it. Are we unique? How did life begin? How did the first structures form? These are fundamental questions JWST is designed to tackle.
And tackling them required a monumental investment. All of this groundbreaking science. It came with a $10 billion price tag, roughly, equivalent to 3.5 billion UAE dirhams or 2 billion Israeli shekels, our sources note.
An immense sum, yes. And it wasn't quick. It took about 2 decades from the initial concept to that successful launch on Christmas Day.
2 decades. Think about the dedication, the challenges. Political changes, budget battles, technological hurdles.
It represents an extraordinary societal commitment, a collective belief across nations and over time in the value of pushing the frontiers of fundamental knowledge, even when the immediate practical applications aren't obvious.
Our sources mention a sense of awe and pride in this human effort.
And rightly so. It involved thousands of scientists, engineers, technicians from NASA, the European Space Agency, the Canadian Space Agency, a massive international collaboration. It's a testament to what humanity can achieve when we aim high, literally towards the stars.
It really makes you wonder, doesn't it? Why do we do this? Why invest so much time, money, and brainpower into looking so far away, so far back in time?
It speaks to something deep within us, I think. A fundamental human drive to understand our origins, our context, our place in the grand scheme of things. It's an investment in knowledge, in perspective, a legacy that extends far beyond our individual lives.
Okay, so we've journeyed from Hubble revealing the vastness to Webb peering back towards the beginning. We have these incredible tools. Let's bring it back to that core question. How old is the universe? How do we actually put a number on it using these observations?
It's a fascinating process, like cosmic archaeology. Scientists combine data from multiple sources. One key piece is measuring the expansion rate of the universe, how fast galaxies are moving away from us, which Hubble first discovered. This is the redshift data.
Right, the faster they move away, the further away they generally are.
Exactly. By precisely measuring this expansion rate, the Hubble constant, we can effectively run the clock backwards to calculate when the expansion must have started the Big Bang.
Running the movie in reverse.
In a sense, yes. Another crucial piece is studying the oldest known objects, like ancient stars in globular clusters. The universe can't be younger than its oldest stars, so they provide a lower limit on the age. And then there's the cosmic microwave background radiation, the CMB. This is the faint afterglow of the Big Bang itself, detected across the whole sky. Studying the tiny temperature fluctuations in the CMB provides incredibly detailed information about the early universe's conditions and composition, which feeds into our cosmological models and helps constrain the age very precisely.
So it's not just one measurement, it's weaving together all these different lines of evidence. Redshift, old stars, the Big Bang's afterglow.
Precisely. It's like a cosmic forensics investigation, using light from different eras and different phenomena as clues to reconstruct the entire timeline. Each observation from Hubble, Webb, and other instruments adds another data point, refining our understanding.
And after all that incredible work, decades of observations, sophisticated modeling, what's the verdict? What is our best estimate for the age of the universe right now?
The current, most widely accepted age, based on the convergence of all this evidence, is 13.8 billion years.
13.8 billion years.
Now, our sources do note that different methods and data sets can give slightly different results, typically ranging from about 13.2 billion to maybe 14 billion years.
Okay, so there's still a little bit of wiggle room. Why the difference?
It largely stems from ongoing refinements and slight discrepancies in measuring the universe's current expansion rate, the Hubble constant. There's a bit of tension between measurements made using nearby objects versus those derived from the early universe's CMB.
The Hubble tension, I think I've heard that term.
Exactly. Scientists are actively working to resolve this tension using new data, including from JWST. But this small range isn't really a sign of fundamental uncertainty about the age. Rather, it reflects the incredible precision science is now achieving, where we're fine-tuning the details and probing the limits of our models. It's a sign of healthy scientific inquiry.
It's actually amazing we can pin it down that closely, isn't it? Getting within a few hundred million years on a timescale of nearly 14 billion years.
It's truly remarkable, a testament to the power of the scientific method and the instruments we've built. And these refinements matter.
Why are those subtle differences important?
Because each fraction of a billion years, each tweak to the expansion rate, can have significant implications for our understanding of the universe's very earliest moments, how quickly structures formed, the nature of dark energy and dark matter, and potentially even the ultimate fate of the cosmos. Getting the number right helps us get the whole story right.
So what a journey we've taken. From thinking our Milky Way was the entire universe just a century ago,
An island universe.
to understanding we live in a vast cosmic ocean filled with perhaps trillions of stars and billions of galaxies, stretching back 13.8 billion years, all revealed through incredible human ingenuity, persistence,
And groundbreaking telescopes like Hubble and Webb.
absolutely, visionaries like Edwin Hubble, monumental engineering feats, and just this relentless human drive to look up and ask, what's out there? How did it all begin?
This deep dive really underscores the remarkable progress we've made, but, it also brings a sense of humility. Every answer seems to open up a dozen new, often more profound questions.
That's the nature of science, isn't it?
It is. The universe continues to invite our curiosity, challenge our understanding, and inspire us to keep reaching, keep building new tools, keep refining our perspective on our place within it all.
We've poured billions into understanding this universe, discovering its breathtaking vastness, its ancient age, and even revealing that ultimate gravitational drain of supermassive black holes that seems to shape the destiny of galaxies over cosmic time. It really makes you wonder, what is it that compels us as a species to dedicate so much effort, so many resources to understanding a universe whose fundamental mechanics, like gravity's relentless pull towards those black holes, seem almost indifferent, destined to eventually draw everything in? And looking forward, with tools like Webb just beginning their work, what deeper truths about creation, about cosmic evolution, and maybe even about our ultimate cosmic fate will we uncover when we can truly see the light from just 100 million years after the very beginning, watching those first stars ignite across the darkness?